So, for today's lesson, we're going to be looking at rotation and inclination of right solids, in this case the tetrahedron. So, the learning intentions for today's lesson are to be able to explain the need of an auxiliary view to find the true shape or true length of an object to solve a tetrahedron rotation problem. The second learning intention is to be able to solve this problem and to construct it to high standard. And finally, the third learning intention is to be able to work efficiently together in groups to solve the problem. So here we're looking at a tetrahedron rotation problem. We're given the plan view of the tetrahedron and we're asked to draw the front elevation, end view, and plan view of the solid. The base is being rotated at 30 degrees to the horizontal plane about the edge 1, 3. So the first thing we need to do is we need to draw a thumbnail sketch somewhere on our sheet and we need to annotate it corresponding to the plan view that we're given. So for instance 2, 0 here represents 2, 0 in our drawing. Following that, we need to project an auxiliary elevation from our plan view. And if we go back to the question here, as specified here, the base is being rotated at 30 degrees to the horizontal plane about the edge 1, 3. So the first thing we're going to do is we're going to draw a line parallel to the line 1, 3. And we're going to project the rest of the points parallel to the line 1, 3. The line 1, 3 is a true length because it rests on the horizontal plane, which is parallel to the XY line. So we'll draw a line perpendicular to the edge 1, 3. So to make that clear, 1, 3 is a true length for the reason that it rests on the horizontal plane of reference. So now the edge 2, 0 will be true length in the auxiliary as it's parallel to the x1, y1 line. The length of this line will be the same as the line 1, 3 in the plan view as it's a true length. And the true length is 80 millimeters. As we all know, a tetrahedron is made up of a triangular pyramid made up of congruent equilateral triangles for each of its faces. So we can simply draw on this triangle by joining up the points and stepping off the true length, which is 80 millimeters, or the same as the true length, taking the true length 1, 3. We're now going to rotate the point 1, 3 on our auxiliary elevation, and we're going to rotate it at 30 degrees to the x1, y1 line. The length of this line be found by rotating point 0 from the center point 1, 3 until it hits or intersects with the line that we've just drawn, that's 30 degrees to the x1, y1 line. The new position of point 2 will be annotated as point C. We now must complete the auxiliary elevation, and as we go back to the definition of a tetrahedron, it's a triangular pyramid with congruent equilateral triangles for each of its faces. So to complete the auxiliary elevation, we need to take the true length which is 80 millimeters, or the length of the line 1,3, and we need to swing an arc from center point C, which we can see here, and we need to rotate point 0 from center point 1,3, or the new annotation AB, and where the two intersect will give us our completed auxiliary elevation. And we can complete our auxiliary elevation by simply joining the 3 points together. The new position of the points 0, 1, 2, and 3 will be annotated as A, B, C, and D. We can now pause the video to discuss why we project an auxiliary view parallel to the edge 1, 3, and why this is a true length. You can now use your augmented reality barcode to help you visualize this. We now must complete our plan view. So the first step is we need to project our lines back to our plan view from our auxiliary elevation. We can now complete our plan view by simply joining the points together and annotating them as A, B, C, and D, as we've just annotated in the auxiliary elevation. They are the new points from the original 0, 1, 2, 3, and they're corresponding, as I just said there, from the auxiliary elevation that we've just drawn. So the next step is to complete our elevation. So we need to project our lines up from our plan view perpendicular to the XY line as shown. We need to transfer and find our lines in the elevation as the line AB rests on the horizontal plane, or the original 1,3 line, and it rests on the X1, Y1 line. It will rest on the XY line. We now need to find our heights from the auxiliary elevation to complete our elevation and end view. The next step is to complete our elevation and end view, as I just said there. So we need to project our points across parallel to the XY line to intersect the line perpendicular to the XY line, which is also known as the X2, Y2 line. So project the lines 45 degrees from the X2, Y2 line up vertical, and the corresponding lines are projected across from the elevation, and where they intersect our points from the tetrahedron, we can then join the points to complete the end view. You can now pause the video to discuss why the heights are taken on the auxiliary. Once we have our views, our points are found from the auxiliary elevation, and we can simply now complete are two views, the front elevation and end elevation, by stepping up the two main heights, H1 and H2, as you can see here, and we'll annotate our front elevation and end elevation corresponding to the annotations that we have in the auxiliary elevation. You have now complete the elevation plan and end view of the tetrahedron, which is inclined and rotated to the principal planes of reference.